So, an example of spring-loaded mechanism would be a cam. In the case of cam, there is a rotatory link, and on top of that, a linear motion link is sitting, which can move in a linear fashion. So, in the present diagram, the link 1, which is a linear link, is held to link 2 by gravitational force. In real machines, you would see a arrangement of spring which is pushing the link 1 down on the link 2 to maintain the contact. So we have understood here the basic building blocks of mechanism formation, that is links and joints. The combination of a link and joint is called a kinematic pair. So a kinematic pair is the basic building block of a mechanism. When various kinematic pairs are connected, the resulting arrangement is called a kinematic chain. So it is formed by connecting a number of links with kinematic pairs such that a definite relation between motion of various links. So we understand the term kinematic chain. A kinematic chain is not much different from a mechanism. Formal definition of a mechanism is that it is obtained by fixing any one link in a kinematic chain. So a kinematic chain is more of a theoretical definition of mechanism formation, and if you fix one link, then a mechanism becomes useful. For example, consider a mechanism here, that is the 4-bar linkage, which we will be covering in much more detail in coming slides. So here, as such, this mechanism, this kinematic chain, is having a definite relationship between motion of various links. So there can be only rotational motion of link 1 possible, and we can determine the motion of link 2, link 3, link 4, all of them. However, if this mechanism just lies in space, it doesn't have any real significance. For getting effective output and to convert it into something useful in a machine, we have to fix one of the links. So we have fixed here the link 4, and then by that this kinematic chain of 4 links became a mechanism. So now we will come to a very important topic from the gauge perspective, which is related to kinematic chain, that is determining degrees of freedom of a kinematic chain. It is also called mobility in some textbooks, mobility of a kinematic chain. Also, this is called Grubler's criterion, or Pushback criterion. This is the method to determine the degrees of freedom of a kinematic chain. So I will be illustrating you a derivation of this criterion. Let us first assume that there is a kinematic chain or a mechanism with n number of links and j number of joints of nth class. So if you recall, well, a little back in our lecture, the joints or kinematic pairs are classified in terms of how many degrees of freedom they are constraining. So a class 1 kinematic pair or joint will allow 1 degree of freedom. A class n will allow n degree of freedom. So if a class 1 is allowing 1 DOF, then it is constraining 3 minus n or 6 minus n DOF, depending on whether you are in 2D or 3D. So in the case of mechanisms, we will see that we will be normally studying planar mechanisms. So we will first derive this criteria for a planar mechanism, that means 2D. So there you have for each link 3 degrees of freedoms. So for n links, the net kinematic chain will have 3n degree of freedoms. So for a link you have 3 degree of freedom, and for a kinematic chain you are having 3n for n number of links. Now a class 1 joint or a kinematic pair will constrain 3 minus 1 is equal to 2 degree of freedoms. The class 2 will constrain 1 degree of freedom. And a class 3 is of course not possible in a 2D system, as it will not constrain any degree of freedom, hence it will not be a joint. So if we have J1 number of class 1 kinematic pair, J2 number of class 2 kinematic pair, then we can calculate the degree of freedom of the kinematic chain as follows. So without the joints or kinetic pairs, or in other words, without any constraining, the kinematic chain is having 3n degree of freedoms. Now the class 1 kinematic pairs will constrain 2 degree of freedom, so we can subtract 2 degree of freedoms for each class 1 joint. So for J1 number of class 1 joints, we have to subtract 2 multiplied by J1 degree of freedoms. Similarly, a class 2 kinematic pair will constrain to 1 degree of freedom, and hence we have to subtract 1 degree of freedom from the total degrees of freedom of the kinematic chain. So 1 multiplied by number of class 2 kinematic pair. So J1 and J2 are numbers. J1 is number of class 1 and J2 is number of class 2. So this is called the Grubler's criterion to determine degree of freedom of kinematic chain. Similarly, for a three-dimensional system, we can also derive the formula for determining the degree of freedom. In 3D, you have 6 degrees of freedom for each link. So, the degree of freedom of mechanism will be 6n for n number of links. And then, if you have a class 1 pair, so class 1 pair in case of 3D will allow 1 degree of freedom and constrain 5 degree of freedoms. Class 2 will allow 2 degree of freedom and constrain 4 degrees of freedom. Similarly, class 3, 4, 5, etc. So, a class 1 pair will remove 5 degree of freedom. So, we have to remove 5 times number of class 1 pairs. Similarly, 4 times number of class 2 pairs, 3 times number of class 3 pairs, 2 times number of class 2 pairs, so class 4 pairs, and 1 times class 5 pair. This is the equation for degree of freedom of a kinematic chain that we have derived here. Now the degree of freedom of a mechanism can be simply derived from this equation itself. As you know, in a mechanism, one link is fixed. That is what the difference between kinematic chain and a mechanism. So, if you have 6 n degrees of freedom of n number of links in a mechanism, one link will be fixed. So, you will have 6 n minus 1 degree of freedoms. So, that's how in a mechanism the degrees of freedom will be 6 n minus 1 minus 5 j1, 4 j2, 3 j3, 2 j4 minus j5, 1 and 2 j5. In case of 2D, the degree of freedom will be 3 n minus 1 minus 2 j1 minus j2. So these are the equations for the mechanism. Now the topic of Grubler's criterion or determining degree of freedom of a kinematic chain or mechanism is very important from the perspective of GATE, because most of the questions from this area are asked based on Grubler's criterion. So let me take you through an example. To illustrate the application of Grubler's criterion, I will draw here kinematic chain. So this is how the questions will come in GATE examination. There will be a sketch of a kinematic chain or mechanism, and then you will be asked to find out the degrees of freedom of the mechanism. Or sometimes you will be asked, in other words, like whether the mechanism is mobile or immobile, or whether the motion is definite or indefinite. So if the degree of freedom of the mechanism is 1, then it is a mobile mechanism with definite relation of motion. If the degree of freedom is 0, it is an immobile mechanism. So we'll just label various links here: 1, 2, 3, 4, 5, 6, problem, there are 5 binary links, 2 ternary links, and 1 quaternary link. However, we do not need to get confused from the nature of the links, because in Grubler's criterion we see only the classification of type of joint, class 1 joint, class 2 joint, etc. There is no consideration given to the type of the link. So there is no need to get confused because of that. A link is just considered as a link. So here we have total 8 links. Whether they are binary or quaternary, doesn't matter. And then we just need to count the number of joints. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 joints, and we have to determine the nature of joint. So in this case, you see that all of the joints are of rotary type, the pin joint, and therefore they are allowing only 1 degree of freedom is allowed by all of the joints. So class 1 kinematic pair or joint. So all 10 joints are class 1. Hence, by using the Grubler's equation for 2D, to recall, the degree of freedom of the mechanism will be 6 multiplied by n minus 1 minus 2 multiplied by class 2, so class 1 kinematic pair minus 1 multiplied by class 2 kinematic pair. Here we have 8 links, 2 multiplied by 10 class 1 pairs. So the result is 1. So hence, the degree of freedom of this mechanism is 1. So likewise, you can pick the correct choice from the given option.